Sue has a very long bio, but it's just a great pleasure to introduce Sue Van Hever as our VIP seminar speaker today. She's the Montfort Professor at Atmospheric Science at Colorado State and joined the faculty in 2008 and has been doing great things ever since. She teaches graduate classes in cloud physics, dynamics, mesoscale modeling, and author of a textbook with her performer advisor on storm and cloud dynamics. And many awards, well deserved, and she serves in many important committees relating to things to do with weather and convection. She's really a world expert on convection, and I sort of challenged her to speak about why the hell we ought to care about convection for the uninitiated non-weather expert. Why do we care about convection, Sue? So I'm going to leave that as your challenge and take it away. And we're all looking forward to this very much.
All right. Well, thanks very much, Graham, for that very gracious introduction and for inviting me to talk here today. It's just awesome to be with everybody. And as Graham said, he's challenged me to why we should really care about deep convection. And so the title of my talk is, So What If Warm Air Rises? Why Should We Care? And clearly, as warm air rises through the depth of the troposphere, it forms these beautiful deep convective storms that are shown in this image. And so my talk today is actually going to be a talk that's given at a very high level view, a 50,000-foot view, if you like, of deep convective storms. And I'm going to start out just with a brief primer on what these convective storms are. And then most of the time in my talk, I'm going to be focusing on these fundamental reasons to care about deep convection. And then if we have a little bit of time at the end, I'll touch on modeling convective storms in the future. Okay, so let's start out with this primer of convective storms. And I just want to get some model jargon out of the way as we begin this. And so as atmospheric and climate scientists, the term with the focus here on the term scientist, we always have to knowledge of storms, right? But also as part of being a weather or a climate scientist, intrinsic to that is an interest in prediction. We want to know what the future looks like, be it in terms of climate or be it in terms of weather. And if we're going to be talking to prediction, this then brings in numerical models. And there's a lot of jargon in and around numerical models. And so let's just touch on that briefly. Numerical models exist across the scales, right? And this comes back to their grid spacing as well as the domain on which simulations are conducted. So at the very one end, we have GCMs or global climate models, and then down the other end, we have these large eddy simulations. Global climate models tend to have grid spacings on the order of about 100 kilometers. They simulate the entire Earth, and typically these simulations are conducted on timescales of decades. Then down the other end, with our large eddy simulation models, these have grid spacings on the order of 100 meters. Their domain sizes are typically on the order of 100 kilometers, and you run these simulations typically for order hours. Now, by virtue of the fact that you're on such fine resolutions in LES models, this allows us to explicitly capture these dynamical motions that I'm going to be talking about. So we can explicitly represent all of those terms that go into predicting these vertical motions. This also allows us to represent in a fully interactive manner these dynamical motions with those processes that form cloud water and cloud ice and precipitation. However, as we go up the scales to GCMs, given the grid spacing in these models, we cannot actually explicitly represent these vertical motions. And so we have to do this implicitly by representing the impacts, right, of what these vertical motions might do. This also means that we are more restricted in the ways in which we can represent the interactions between those microphysical processes, those processes that make cloud water and cloud ice and the dynamics. And then in between these two extremes, we have regional climate models and cloud resolving models. And so hopefully this gives you some sense as to the range of models we have available to us, as well as the strengths and weaknesses depending on the platform that we use. Okay, let's look at some convective storm processes now. And I'm going to look at this by using this webcam animation on the development of a deep convective storm, where each of these images...
Just as we watch this, I should have mentioned in the outset, if you have questions, we're going to pose them in the chat, and we'll get to them at the end, rather than cut in during the talk. So I'm sorry, Sue, but
no, it sounds great, no problem. So I'm going to use this animation. And so if we have a look at this and we start this out, something gets convection going on early in the day, and we refer to this process as convective initiation. And there's still a lot we don't actually know about what gets these little germs or seeds of initial convection going. However, we find that if that does get going in what we refer to as a supportive convective environment, then we find that warm, moist air will rise. And so if you could sample in some of these plumes that we see here, you would find that the air is warmer and moister than the air in the environment. As these plumes rise, though, they tend to mix in air from the surrounding environment. This air is drier, and as a result of that, this mixing with the environment in these processes called entrainment, you see that this mixing results in air that's colder and drier, and that colder, drier air will then sink. Another thing to notice is that these storm systems are comprised of multiple thermals, and that these thermals actually moisten the air, allowing these storm systems to build to really tremendously great heights. And as they reach up into the upper levels of the atmosphere, they produce these large umbrella-like clouds or anvils, and these anvils have a lot of ice processes on the go with them. So we see the development of these large umbrella anvil type clouds. And then ultimately, after all of this dynamical interaction, we will see the production of rainfall and or hail and other ice species at the surface. So this gives you some sense of the importance of the rising of warm, moist air, of these mixing processes, and of the fact that these deep storms are comprised of multiple thermals, not just one big updraft. Whoops. All right, if we look at the different kinds of convective storms that we can get, as we've seen already, they are driven by buoyancy. This warm, moist air is more buoyant than its surroundings. We also know that vertical pressure gradients are important in driving these systems. These systems form over oceans, over land. They form in the mid-latitudes, in the tropics. And really important to these systems is that they include both the liquid and the ice phases of water. And then they take on this really wide range of shapes and sizes. They can be circular, they can be linear, they can rotate, they cannot rotate. And all of these different characteristics then talk to, in essence, storm longevity, how intense these storms can become, and the kinds of weather that they can produce. Now, the spatial and temporal scales in convective storms are enormous. And so if we look starting down here at the bottom of the sizes of those little particles that are used to grow cloud droplets, these are on the order of 0.1 microns. Then as we get to a cumulus cloud, say, let's assume a length scale of 1 kilometer. They can be larger, but let's assume a length scale of 1 kilometer. And this means that the length scales between these little aerosol particles and the size of a regular cumulus cloud is on the order of, this is like 10 orders of magnitude different. And if you get to larger convective systems, this can actually go up to 13 orders of magnitude. So what does 10 orders of magnitude in spatial scale look like? If we assume that the orbit of the moon around the Earth corresponds to the length scales of a cumulus cloud, then 10 orders of magnitude down takes you to the size of an oak leaf. And so these are the kinds of spatial scales we have to consider when we're wanting to simulate or represent or study or observe all of these processes pertaining to convective storms. And so this makes then for a very challenging scenario when it comes to, as I said, modeling, or if we want to make observations through remote sensing, or if we're wanting to conduct laboratory research on those processes that build convective storms. Okay, so that was sort of a primer about the processes that build convective storms, and I now really want to move into these 5 reasons as to why we should care about convective storms. And if we go back to sort of our pioneering scientists, to Aristotle, the only possible way to understand phenomena was to know their purpose. So we really need to get to the purpose of convective storms. Galileo, who then put science at a whole new level through the development of the scientific method, realized relatively early on that progress is often achieved through correct decisions as to which questions should be asked. So we need to understand the purpose of the storms, and we need to ask the right questions about them. And so the first reason we should really care about convective storms is this the idea of vertical transport, right? So these storms facilitate vertical transport in the atmosphere. Vertical transport is sometimes referred to as vertical velocity, or just W, or updraft velocities. It goes by many terms. facilitated by the presence of these storms. And so if you took a cross-section through one of these deep convective elements, as shown here, you can see that by virtue of the motions through these storms are able to link and transport warm, moist air from the boundary layer all the way up through the depth of the troposphere and into the upper levels, where they spread out to form these large anvil clouds. At times, these motions can even transport air into the stratosphere. And storms don't only transport air upwards, they also transport air downwards. So they will bring upper tropospheric air down to the surface. So convective storms are the big vertical mixers of the atmosphere. And they vertically transport not only water, but also energy and momentum, trace gases, aerosols, and so on. This here is an example of smoke being transported by a deep convective storm. You can see smoke here in the lower portion of this image and transported all the way through the depths of the storm and then detrained in the upper levels of the troposphere. Okay, now as a community, we have a pretty good understanding of the vertical momentum equation. We know what goes into it. It's shown here, and I'm not going to focus on this for too long, except to say that if we're trying to predict, right, the vertical velocity or this transport or these upward motions, we know that we have to understand how it's moved around in the horizontal and in the vertical. We know that vertical gradients in pressure help to drive this transport. We know that buoyancy, which we've already touched on, is also really important. It has a thermal contribution, so this is our warm air. It has a water vapor contribution, so this is our moist air. And then it has a condensate contribution, and this really talks to the amount of mass that a rising column of air needs to carry around. And then finally, there's also this diffusion term, or this entrainment term, or this mixing term. Now, we have a pretty good understanding, as I say, of all these terms and how they contribute to the time rate of change of this vertical transport. And if you look to see these different terms, you will see that they are impacted either by the environment or by those processes that form cloud, water, and rain within storms. So advection is impacted by the winds in the environment. The pressure gradient is impacted by the pressure in the environment, as well as some of latent heat release. This buoyancy term comes back to microphysical processes through this vapor term, through condensing vapor to make cloud droplets, through the release of latent heat, which impacts this thermal term. And then diffusion comes back again to the properties of the environment. And so the important take home from here is that the dynamics, or this transport within these systems, is strongly impacted by those processes that make precipitation or make cloud droplets or ice crystals, as well as the environment in which these storms form. And so if we're going to understand and hence predict these vertical motions, we really need to understand environmental properties and all these microphysical properties. Okay, so let's just look briefly then at environmental controls. And as a community, we have a pretty good sense of the fundamental environmental characteristics that are important to deep convective storms. The first is CAPE, or convective available potential energy. It talks to the energy available in the environment that storms can draw on. We also know that the manner in which winds vary in the vertical is important to these storms. And we also know that low-level moisture is really important to these systems. So that's great in theory, but when we start looking at things in practice, and as we did when we went out into the field recently, we were focused on storms of a similar type. These are supercell storms. And when you start to look at the environmental temperatures as shown here, or the environmental moisture, we can see great variations in these environmental properties, even though the storm that's being formed is of a similar type. We could also see that for these storms, the CAPE, or this energy available, vary tremendously once again, even though the storm type being formed is similar. And so while we understand basically what the role that the environment plays, there are a lot of complicating factors. We don't actually really know which factor is the predominant factor or what the appropriate combinations of these factors are. Convective initiation, or how this convective process gets started, is still quite a mystery to the community. Entrainment is challenging, right? This mixing of the environmental air into these vertical updrafts, or this transport of air in the vertical. And then just to add to this, storms actually change their local environments. Remember that in that animation I showed you, we had those multiple thermals going up, moistening the environments, which then allowed thermals to develop even deeper. So there's a lot of complicating factors as we try to understand the environmental controls on deep convective storms. This leads to problems such as demonstrated in this image here. If we compare regions over equatorial Africa with regions over equatorial South America, these are both continental regions in the tropics, right? And they have relatively similar environments. And yet, if you look at the cloud top heights of the storm systems developing here, as indicated by the heights of the 40 dBc reflectivity contours, we can see that these are relatively intense storms by virtue of the height. They exist between 14 and 19 kilometers above the ground, whereas if you look over here in equatorial South America, they are not as intense. They do not get as deep. And the big question then is why? Because certainly at first glance, these environments should be relatively similar. The same can be said for tornadoes for storms that produce tornadoes or don't produce tornadoes. We know that the low-level wind shear, as well as the low-level thermodynamic environment, which gives us the height of the cloud base, are really important to these supercell storms that produce tornadoes, but we don't really know the right combination that makes some of these storms produce tornadoes or do not produce tornadoes, as you can tell from the scatter of the tornadic and non-tornadic storms across this plot. And so atmospheric environmental properties, we know that they fundamentally impact these vertical motions or this vertical transport, but big gaps exist in our understanding of this transport. And as such, a unified theory of the control of the environmental properties on vertical transport simply does not exist. This then has led actually to the Academy's decadal survey to classify as one of their most important objectives this question as to why do convective storms, heavy precipitation, and clouds occur exactly when and where they do. Okay, so that talks to the environment. The other thing that we said was really important are ice processes, or excuse me, microphysical processes, those processes that form cloud droplets and ice crystals in clouds. Arguably, as a community, we have a relatively good understanding of microphysical processes in the liquid phase, but when it comes to the ice phase, we have a lot of work to do still. The ice phase is complex and comes about in part because there are a lot of different ice particle shapes and types. These can vary from simple cloud ice all the way through to snow and hail. And the various processes and pathways forming these different ice particles vary tremendously. This makes it difficult to decide which deterministic pathways we need to be on to achieve an end ice crystal. Another thing that makes studying ice very challenging is the different shapes and sizes that they take on, as well as the density of ice crystals. The density of ice can vary by an order of magnitude, whereas we're very comfortable with the density of liquid water. You may say, well, why should I care about the density of ice as well as the shapes? This has a significant impact on how fast ice crystals can grow, as well as how fast they can fall. And so this then talks to the extent of our convective anvils, which we will talk about. It also talks to the extent of how easily we can remove ice from these transporting updrafts. And it also talks to the extent of the amount of energy we can release by virtue of condensing or freezing vapor onto these ice crystals. So this is a really important element. And what I haven't and won't have time to touch on is the generation of secondary ice particles that also makes studying ice processes really challenging. Now, that talks to shortfalls in our theoretical understanding of the environment and of ice processes. And of course, such shortfalls in theoretical understanding translate to our models. Remember that numerical models are really just fancy calculators designed to solve partial differential equations. And so we cannot represent those things we don't understand. And this has become evident in some of our models. So if we look at the top row here, these are our cloud resolving models. These are those models that explicitly capture these vertical motions. In the study from Warble et al., which compared model simulations of these vertical updraft velocities with those derived from Doppler radar, we see substantial differences in these simulations of TWP ice on the order of 200%. In a more recent model intercomparison project, which we finished up just this year, we compared the updraft velocities produced by 7 state-of-the-art cloud-resolving models. We were simulating isolated convection, developing in and around Houston. And you can see that while these predicted velocities in the warm phase of the clouds, where we're making cloud droplets and things, are relatively comparable, as we get into the upper levels, the differences become much more substantial. And the differences between models and the differences between the models and ops in these two different case studies is often attributed to the interactions between these dynamical flows and the ways in which we represent ice. If we turn our attention to GCMs, right, these are these models where we now have to parameterize or represent this vertical motion. We know that our parameterizations are often designed in and around environmental properties such as relative humidity, but you can see that depending on these environmental conditions, there's a wide range in the amount of mass that's transported in the upper atmosphere. However, we don't really have a good understanding as yet as to the roles played by relative humidity, and so we have to question then how accurate or how appropriate this is. And even when we get into regional climate models or simulations, these were run using the WRF model, where we use parameterized vertical transport, simulating case studies, right? The same case study, but just using different ways in which we represent this vertical transport leads to great differences in convective mass flux. So we have our work cut out for us when we want to represent this transport in models. Right, what about this transport then in future climates? And Marty Singh and Paulo Gorman and their various co-authors have done quite a lot of work in this. They've run global climate models as well as regional climate models. And they've found that with global warming, that CAPE increases, but it increases at a much faster fractional rate than the vertical velocities themselves increase that. And this talks to the role of things like the environment, entrainment, this convective initiation, as well as these microphysical dynamical interactions, many of which cannot be captured in global climate models. As they got down to sort of regional climate models, they certainly found that this vertical transport or these vertical velocities increases as the climate warms. And the really interesting thing about the study was that they find, as shown in this figure, that these increases, right, tend to occur higher and higher in the atmosphere in warmer and warmer climates. This means that if we're really interested in understanding what goes on in this transport throughout the atmosphere as the climate warms, we need to be investigating what's going on in the upper levels. So if we want to go after these dynamic changes in future climates, we really need to be looking at storm systems in the upper levels. This is a bit of a kicker because if you go back to some of the earlier global climate predictions in terms of where we see the greatest sensitivity to precipitation changes, these tend to occur in the lower levels where we have warm phases producing precipitation, or where our precipitation processes are simply based on the liquid phase. So this gives us some sense that if we after how precipitation changes in future climates, we then need to be looking into the lower levels of these deep convective transport systems, whereas if we're interested in the dynamics, we need to look higher up. Okay, so that was the big one, vertical transport and how it's facilitated by storms. And that vertical transport then talks to the four of the next reasons I want to look at. And so the next big reason to study and understand storms is the role that they play in the large-scale circulation. We know that in the tropics, right, these are a source of energy for the broader planet, and much of the pioneering work on this topic was done by Riehl and Malkus in 1958. And so by virtue of their calculations, they were simply armed with a few radiosondes and some theoretical calculations of the moisture and energy budgets between the tropics and the mid-latitudes. They worked out by virtue of their calculations that there's a net import of moisture into the ITCZ in the lower levels, and that there's a net export of energy out of the ITC in the upper levels. And they correctly assumed then that within the regions of the ITC, you needed this upward energy flux. And so the questions that they then asked was what was going to facilitate this upward energy flux. They had a good understanding of the profiles of moist static energy in the tropics, where moist static energy just represents the energy available both from sensible heat, from latent heat, and from by virtue of geopotential height. So they knew that this energy available was constant in the lower levels, that it decreases with height, and then in the upper levels, it increases with height. And so, as I said, they were going after what facilitates this upward energy flux. And they had three different ideas that they thought about that could do this. They looked at diffusion, right? But they reasoned that diffusion could not bring energy into the upper levels if you have this minimum in the mid levels. So they got rid of diffusion. They looked at large scale lifting, synoptic scale lifting, but they reasoned that this would mix out these profiles. And so ultimately, they came down to the explanation as being this lifting or this transport that occurs within these deep convective storms. And so under this scenario, they argued that these storms would take energy from the lower levels, that they would not mix, so they were protected in the mid levels, and that they would transport this moist static energy to the upper levels. This was a fundamental finding. And if you go back to their paper, they actually state in there the most striking conclusion from this work is, in fact, that summing for this 10-degree belt around the globe, you only need on the order of 1,500 to 5,000 active giant clouds, which are these active deep convective systems, if you're going to maintain the heat budget of the ITCZ, and hence provide implicitly much of this poleward energy export. The take home from this, deep convective storms play an incredibly important role in this energy flux that we see in the tropics and assist in driving the Hadley cell circulation, which of course determines regional and global climates. There was some discussion subsequent to their work about this term protected. Remember when we looked at this earlier, this animation of deep convective storms, we saw this entrainment or this mixing on the go. Ed Zipser helped reconcile some of these ideas in 2003 in showing that the latent heat released by ice processes, which hadn't been considered, actually is able to offset these entrainment effects. And then some modeling studies since then, including a study that came out of our group, actually investigated this. What we did was we ran thousands of trajectories through simulated tropical convective systems, and we looked at the profiles of equivalent potential temperature. This is a very similar thermodynamic variable to moist static energy that Reel and Malkus had looked at. And so if you look at how this theta E varies in and along these trajectories, we can see that in the lower levels, there's high values of this theta E, of this moist, warm air. As you get to the mid levels, by virtue of these entrainment processes, you see this decrease. And then by virtue of the role of ice processes, you see these higher values again of equivalent potential temperature. We looked at the number of these low-level trajectories that made it all the way up into the upper levels, and those that did make it had a significant contribution by ice processes. Okay, so we've looked at the role of deep convective systems in vertical transport. We've looked at the role that they play in the large-scale circulation. The next deal or important thing is the role that deep convection plays in cloud-radiative forcing. And so we know, and we saw up front, that deep convection produces these really extensive anvils at their cloud tops. And if you look at this optical flow imagery, which we're looking down on one of these convective anvils, you can see the presence of the updraft here that's transporting all of this mass up toward the tropopause. As a result of reaching the tropopause, this mass gets detrained or spread out. And these red lines here are indicative of that diverging mass field. Clearly, the stronger this transport through these updrafts, the more mass will be detrained into these anvils. Now, we know that upper level clouds are really critical, right, for cloud radiative forcing and hence future climates and the radiation budgets of the current and future climates. And so some studies done both by Jay Mace and Steve Massey in the early 2000s demonstrated that about half of these tropical upper level clouds have been associated with deep convection at some point in their lifetime. So these deep convective storms are really important in producing these upper level clouds. Why do we care about that? Well, we know that these upper level clouds or these ambles modulate Earth's energy balance. And so we know that solar radiation clearly warms the surface as well as the atmosphere, and that the re-emission of long-wave radiation then cools the planet. Now, re-emission of long-wave radiation occurs at the temperature of the body that's re-emitting it. So deep convective clouds also absorb long-wave radiation and re-emit it, but they re-emit it at the temperatures, right, at cloud top. And so as a result of this, they absorb more than they re-emit. And so they have a warming impact on that column. So this is referred to as the greenhouse effect. Deep convective anvils also scatter incoming solar radiation, which actually has a cooling effect. And so there's some tension here between these cooling and warming effects associated with deep convective anvils. And it's the properties of anvils which then determine which of these effects are dominant. So if we think then about cloud radiative forcing and how these anvils then might change in warming climates, convective anvils are actually expected to occur higher up, and they're actually expected to decrease in area, as shown by this really nice study by Sandrine Boney and co-authors. And this is due in part to a reduction in updraft velocities and to changes in the upper level static stability. Remember, these predictions are coming out of GCMs. There may be some observational support for this. This comes from some work that Matt Eigel and I did a number of years back, where we looked at cloudsat convective objects and how they might vary with increasing sea surface temperatures, which we can take as a proxy for warming climates. And we see that as we get to warmer sea surface temperatures, so the extent of these convective anvils as well as their heights, the extent tends to decrease and their height tends to increase. So this does suggest that these predictions by these GCMs may be rooted at least somewhat in current observations. However, the important thing to remember is that while GCMs capture many of the pertinent processes pertaining to climate and radiation and so on, they do not capture these small-scale dynamic motions, how they are impacted by the radiation, and all the links and feedbacks between these dynamic motions and the microphysical processes that actually go to control the extent of these tropical anvils. And in this great paper by Dennis Hartmann, he states in there that our key goal really should be then to understand what processes control the relative abundance of optically thin and optically thick anvil clouds. And so optically thin clouds, we know, will warm more. Optically thick clouds will warm less. And so this question that Dennis Hartmann has posed is really, what are those processes that determine whether these anvil clouds are optically thin or optically thick? We know that the optical depth of clouds is determined in part by the amount of condensed water, this can be liquid or ice, that's contained within these anvil clouds, as well as the size of the particles within these anvil clouds. Well, what gives rise to these, or what drives these? First and foremost, vertical transport is critical, right? It's that determines how much water or how much ice is lifted and detrained into these anvils. Also, the environmental conditions talk to how much water was in the cloud in the first place, or to how deep the cloud can grow. And then clearly ice processes, including aerosols, are really critical to determining both the size and the numbers of ice crystals in the anvil. This here is an example of the role that aerosols might play on anvil particle sizes. This is an example of a deep convective storm, which is ingesting smoke from a large forest fire, and you can see it's transporting the smoke up and in through the storm system and detraining it at its anvil level. And so a number of years ago, Dan Lindsay and colleagues tried to quantify this process a little better. They looked at this case study in 2009. A deep convective storm was developing here in and along the dry line. And on this day, as these storms were developing, there was a lot of dust and smoke being lifted into the environment. So later on, when the storm actually develops in and along the dry line, you can see by virtue of the building up of smoke and dust behind the storm system, that this storm system actually ingested or sucked in or took in quite a lot of these smoke and dust particles. If you now use satellite imagery to look in essence at the effective radius of these particles or the sizes of these particles, earlier in the day, which is really this storm system here, you could see that the size of the ice particles right at the top of the anvil was on the order of 40 to 50 microns. But for those systems that developed later, this animal here, that it sucked in all of this smoke and sucked in all of this dust, the size of these anvil particles are now down to an order of 10 or 15 microns. They compared that day, which is this observed line in terms of these ice crystal sizes, with the climatology for this region. And on this day, it's clear that by virtue of the presence of these smoke and dust particles, that these ice sizes were shifted way down in the size spectrum. This, of course, is going to talk to the optical thickness of our convective anvils. We can also look at the importance of ice crystal sizes and how fast they fall in using numerical models. And this is something, of course, that GCMs cannot necessarily capture or represent, but which are important to determine the extent and the thickness of these convective anvils. So we're looking down on the anvil here. This is a plan view of a convective anvil developing, and this is the side view of it. And what we did was this was work we did with Eric Jensen. We interfaced a very sophisticated ice particle growing model where you can look at each of the ice particles. We interfaced that with a cloud resolving model so we could get information on the dynamics in the environment. The take home from this, as we look down on the anvil after releasing these particles and watching them grow, is that smaller particles, represented by these blue colors, travel further out or travel further away from the updraft than do larger particles in these red colors. And smaller particles also fall less fast than do larger particles shown here in red. And so in time, we are left with anvils that are large in extent, that are comprised of small particles that do not precipitate out relatively quickly. And as such, we're left with these convective anvils that live for a long time and that are comprised of lots of numbers of small ice crystals. This again, of course, talks back or comes back to the optical depth of anvils and whether or not they are optically thin or thick. Okay, so that was the third reason. The fourth reason to care about deep convective storms, as well as the fifth, are really those that we are pretty much aware about simply by living life on Earth. The first is that these storms play a really important role in producing fresh water. Steve Nesbitt showed us this in terms of the fact that these organized convective systems produce 70, 80, 90% of the rainfall within the tropics. And Courtney Schumacher and others demonstrated that whether the precipitation comes from the deep convective core itself or is produced by these anvils, this plays a really important role in setting up or establishing the profiles of energy in the environment. A more recent paper by Chantal Liu and Ed Zipser looked into the size and intensity of what they called precipitation features. And they looked at the contributions of these different precipitating features to the global total precipitation. And they found some interesting things. Firstly, if you look at the size of these features, 70% of the total global precipitation is produced by the top 1% of storms in size. So a lot of our precipitation comes from very large storm systems that are not as frequent. However, if you look at the same thing and look at this in terms of precipitation produced by intense storms as given by the height of the 40 dBz ecotop, we see that as you get to these really intense storms, storms that have cloud heights of ranging around 10 to 18 kilometers, these really intense storms do not contribute significantly to the global total precipitation budget. And rather that more of this global precipitation comes from storms that are more moderate, storms that have cloud top heights varying from 5 to 8 kilometers. So there's a disconnect here in the sense that precipitation is produced more effectively by moderate storms, and our really intense storms do not produce precipitation as effectively. that was investigated further in this paper by Hamada. What's shown here is the fraction of storms that are both dynamically intense and produce a lot of precipitation to the total of storms, whether or not they're dynamically intense or produce a lot of precipitation. And you can see that particularly over the land masses, those storms that are both dynamically intense and have strong updrafts and produce a lot of precipitation only comprise about 10% of this fraction. So take home from this, dynamically strong storms are not necessarily your big producers, right, of precipitation. It's more about moderate convective storms that produce that produce lots of precipitation. This is also evident in cloud resolving models. This comes from a cloud resolving model database where we're looking at the maximum updrafts, the relationship of high rain rates to these maximum updraft velocities. And you can see that while to first order storms need to be sufficiently strong to produce strong rainfall, this is certainly not a one-to-one relationship. To add to this, what makes this more difficult is that we still battle to do well with producing precipitation, even in our most sophisticated models. This comes back to that model intercomparison project I mentioned earlier, where we were looking at 7 state-of-the-art cloud resolving models and simulating this isolated convection around Houston. And what's shown here is a time series. The different colors are the different models. And then this black line is the stage 4 precipitation observations. The take home from this is that, firstly, there's a huge difference between these state-of-the-art cloud resolving models in terms of the amount of precipitation produced. And secondly, most of the models actually underestimate the accumulated precipitation by 40%. So we have our work cut out for us when it comes down to properly and appropriately representing fresh water. Finally, the last reason to care about deep convective storms is severe weather. And severe weather can mean anything from tornadoes to large hail. It can mean lightning. It can mean flash flooding events. And we know, as I say, simply by living on Earth, that storms produce severe weather. So we are aware of the dangers that they can bring about. However, this has also now started to catch the attention of the World Economic Forum. They put out these annual reports in which they look at events which will have great impacts on life on Earth, as well as the likelihood of them occurring. And if we look up here in this top right quadrant, and we zoom in on that a little bit, we can see here extreme weather sort of is front and center in this regard. Now, extreme weather and severe weather are not necessarily the same thing. Extreme weather really means weather that's happening perhaps at a more intense level or more often than is normally expected. Certainly, if we start seeing severe weather becoming more intense or happening more often, it is then classified as extreme weather. So this can be seen, the impacts of more intense and severe weather can be seen in this recent publication from NOAA that looked at the number of billion-dollar events, inflation adjusted per year over the last 40 years. And you can see that 5 of the 6 most intense years actually happened in the last 5 years. So it does seem that these extreme weather events are on the up. This can be represented in another way in this schematic in terms of billion-dollar weather and climate events, right, that happened in 2019. 13 out of 14 of these events were associated with deep convective storms. And then how are these severe weather events likely to change in the future? And there's been more and more work being done on this. This study conducted by Jeff Trapp and co-authors used global climate models to look at how severe storm parameters may change in the future. And they show that in the spring and in the summer months, we see increases in CAPE and the low-level humidity. We do see some decreases in vertical wind shear, but if you look to see the number of severe storm days, these are on the up with warming climates. Remember, in GCMs, however, you cannot simulate individual storm events, right? These are just the environments that may support those. I'm honing in on scales and looking at flash flooding events. This was some work done by Doughty and Rasmussen just last year. And they were looking at how flash flooding events might change in future climates. And they were using convection permitting or cloud resolving models. And they compared a control run, which is in and around this decade, with a pseudo global warming run, and they found that the amount of rainfall per flash flooding produced storm actually increases in these warmer climates, and more than that, the runoff also increases. And so we may expect flash flooding events to become a lot more intense and a lot more dangerous as the climate progresses. Okay, so hopefully I've convinced you that there are 5 good reasons to care about deep convective storms, and maybe you latched onto 1 or 2, hopefully all 5. As we look to the future, though, let's look to see what modeling convective storms holds in the future, or what we need to do, or what we need to be concerned about. And so if we come back to Galileo's true philosophy had to be a judicious mix. Galileo stated true philosophy, or true science, philosophy and science were equated at that time, had to be a judicious mixture of observations, reasoning, and mathematics. Now, a lot of you in this audience work in the observation world. Hopefully, good reasoning is incumbent on all of us. And then this mathematics element, I would argue, is our use of numerical models. Remember, as we said earlier, models are simply fancy calculators to solve partial differentiation quickly. And so if we look at models in the future, we've made a lot of progress over the last 3 or 4 decades. We've certainly seen that for global models. We've gone from grid spacings that are order hundreds of kilometers all the way down to current grid spacings are several kilometers, 4, 5, 6 kilometers. And for our LES models, these process models, their model domains have increased from being about 1,000 meters or 1 kilometer all the way up to about 1,000 kilometers. If we look to the future, then we know that grid spacing and our capabilities are really dependent on future computational capabilities. And if we look at this plot here, even if we assume that our doubling time of computational capabilities is less than Moore's law, this suggests that in the next decade, all of our models really, our GCMs as well, all should really be using 1 kilometer grid spacing. In this wonderful article by Christoph Schaar in Bands last year, he and his co-authors focus now on the development of 1 kilometer scale GCMs, right, where this is the target. And in essence, they talked to what we have readily available right now. So on this plot, in this upper corner here, we're getting to global models that have grid spacings on the order of 1 kilometer. Right now, we certainly have regional climate model simulations that extend beyond 10 years, as shown here. We certainly have global climate model simulations that extend beyond 10 years. These are really the MIP models. And then up in this corner, we have these prototypes where we have these 1 kilometer GCM simulations, not for as long a time periods, less than 10 years, but nevertheless, there's a lot of work being conducted on this. And he states in his paper that this increase in resolution, right, this move to 1 kilometer GCMs represents a quantum jump in climate modeling, as it allows us to replace the parameterization of moist convection by an explicit treatment. So this allows us now to actually predict and represent all of those processes that drive the rising of warm and moist air. There's a lot of action that's been on the go with these 1 kilometer global models. Diamond is really the first intercomparison project of global storm resolving models. They had 9 models conduct simulations for 40 days on this 1 kilometer grid spacing. You can see some of their results shown here. And if you look at their global renditions of their cloud fields, can you tell by looking at this which is observational data from Himawari? It's actually this one. But the point being is that, you know, these global models are doing a really good job when run at 1 kilometer resolution in representing cloud fields and cloud processes. Also, you may have heard of this terminology, the digital Earth. The European Union is now building a digital twin of Earth, really to revolutionize climate forecasts. It's in under this project called Destination Earth, and they are developing, again, these 1 kilometer global climate models that incorporate all sorts of processes from the atmosphere through the ocean and the land. These models are exascale models. So what does that mean? That means that they are able to conduct 1 billion floating point operations per second. They come at the cool price of 8 billion euros, these efforts, And these models will assimilate more observational data than ever before, including things like air pollution, crop growth, forest fires, and so on. And they make use both of traditional CPUs and graphical processing units, which really help speed up our models. So all of our problems are solved then, right, as we move to these 1 kilometer GCMs. Unfortunately not, right? And our regional climate models that are run on these high resolutions demonstrate there's still sort of 3 biases remaining that will need to be addressed. The first is we still see persistent microphysical biases. These are images of model reflectivity minus observed reflectivity for different case studies simulated with different microphysical schemes. And you can see that in most of these scenarios, we have this reflectivity high bias in models. This is due to our hydromedias typically being too large, and this is often associated with rhyming processes of ice. These differences really come back to the fact that we are under-parameterized in representing these cloud processes, these microphysical processes, and that we're not properly capturing convection at 1 kilometer. We also still need to get back to how this might vary in the environment, different environments. There's this convective dynamics bias. This comes from some work done by Adam Varble. This is for the same case study. It's a cross-section through a deep convective storm. The grid resolution here is almost 1 kilometer. The grid resolution here is 100 meters. When we add 1 kilometer, our updrafts are too broad and too strong. And this means that we cannot properly or accurately represent this transport element appropriately. When we get down to 100 meters, our updrafts occur in these chains of thermals that we saw right at the beginning of the talk. They're much narrower, they're much smaller, the velocities are less by virtue of the fact that they're more susceptible to entrainment, and these more appropriately represent transport. And then finally, even when we're using our LES models, do we really have appropriate observations with which to evaluate them? LES models are doing a good job on these grid spacings of 100 meters, but we really are in need of observations in different environments for different parts of the world. So if you look at this work recently produced or published by Wang et al. And co-authors in 2020, what they looked at was vertical profiler updrafts, both in the Amazon and in Oklahoma regions, versus those updrafts simulated by models at 1 kilometer grid spacing and at 250 meters. And when we add 1 kilometer grid spacing, at least compared to vertical profiler updrafts, we can see, right, that our updrafts are too strong, whereas when we're at 250 meters, they're much more comparable to the observations. We also see that our updrafts are too wide when compared with the observations. So we need observations of updraft strength and structure. We also need to be able to track these observations in time. So if we go back to this model intercomparison project in and around Houston, where we were looking at all of these isolated updrafts using these 7 state-of-the-art cloud resolving models, this shows here the various cells within one of the simulations and how long they live for. And if you can track both the dynamics in time, as well as things like the hail mass and the total condensate mass in time, we can see that there's quite a variation in the dynamics, there's quite a variation in the condensate fields. And more than that, as we started out at the beginning, the microphysical fields max out after we max out in the dynamics, right? So we need to understand the links between the microphysics and the dynamics and how these evolve in time. And so with that, I have now really sort of come to the end of my presentation. Just summarize what we talked about a little bit today. I gave you a little primer about convective processes, and then try to convince you of 5 reasons why we should care about convective storms that are formed by virtue of this rising of warm, moist air. We know that convective storms play a critical role in vertical transport. They link the lower levels with the upper levels, and they vertically mix the atmosphere. We know that deep convective storms play a critical role in large-scale circulations. Remember, they help to drive the Hadley circulation. They help to transport energy between the tropics and the mid-latitudes. In driving that Hadley circulation, this determines regional and global climates. And we have to ask the question, what happens if we're changing these deep convective storms in changing climates? What impact does that have on large-scale circulations? We know that deep convective storms are really important in terms of their production of these upper level anvils, but it's the microphysics as well as the intensity of the dynamics that determines whether these anvils are optically thin or optically thick, and hence have important implications for cloud radiative forcing. We know that these systems produce fresh water, and that most fresh water appears to be produced by moderate convective systems as opposed to the most intense systems. And then finally, they are important producers of severe weather, which seems, at least by our climate model predictions and our regional climate models, going to be becoming more intense in the future. I hope I've convinced you of the significant role of the environment and ice processes when it comes to deep convective storms, that we have a long way to go in terms of our theoretical understanding of our capabilities in measuring these processes, as well as our capabilities in modeling these processes. And then even as we take this amazing quantum leap, right, getting to 1 kilometer GCMs or our global climate models, we will still have work to do in terms of enhancing or improving our representation of those processes important to deep convection, including the dynamics and the microphysics. And so with that, I'll stop and thank you for your attention.
Thank you, Sue. Applause, applause. Yes, thank you very much. I will take questions now. Okay, so let me scan through the chat.
Let me just, yeah.
Andreas, you have a question about role of importance of soil moisture to analyze convective systems. Yeah, Andreas, do you want to open up your mic and ask the question?
Sure. Yeah. That was my question. What's the how important is the soil moisture for these convective systems, and then what are the temporal and spatial requirements for knowing the soil moisture so to be useful?
Yeah, Andreas, this is a great question, and quite a lot of work is now being done into the role of soil moisture. It certainly plays a really important role in that initiation or those processes that seem to start convection. We can see new convection developing along gradients in soil moisture, for example. So we know that it's important to that. We also know, for example, that the intensity and frequency of these large organized systems over the continental US, for example, when trying to simulate those, we know that they're really dependent on accurately and appropriately measuring or representing soil moisture. And clearly soil moisture is really critical to moistening the low-level boundary layer. So to get that into spatial scales that are important, these storms can be initiated along really fine gradients in soil moisture. So I would argue that we need scales in soil moisture that certainly approximate the convective scales of those initial storm systems. So order several hundred meters going a kilometer, a challenging task, no doubt.
Great, thanks.
Thanks, Sue. I mean, obviously, the hour is almost up, but I will keep this open for as long as anyone wants to hang around. That's all right, Sue, to ask questions?
Yeah, that's totally fine.
Okay, so Tom offers a real broad congratulations, and in my words, he's sort of indicating that probably Herb Reel and Joanne Simpson would be smiling down upon you. So that's my words of Tom's comment. Evan, you have a question? Do you want me to ask it for you? I guess I can just ask it for you. Can you?
I actually, it's a multi-part question. Go ahead.
You better ask it, Evan. Evan, you ask it, because it seems I don't think I'd do it justice.
Okay, so you started off, you showed an animation where you looked at the evolution of cloud particle size. But since you mentioned that the density of cloud particles really depends a lot on habit, have you looked at how the habit distribution varies with time and space within the cloud?
Yeah, so that's a great question, actually, and it really talks then ultimately to how long anvils live and to size distributions of ice particles within these convective anvils. And so I think perhaps even just going back to that animation I showed, let me just see if I can pull it up here. let me just put this into display mode. If you look at this, what this is ultimately showing, if you look at the side of a convective anvil, is that in the upper levels, by virtue of the fact that different habits or different shapes or different sizes of ice crystals fall at different speeds, and they often have different ice densities, over time, as these storms develop over time, you're left with the smaller ice crystals at the top, right, at the top of the anvil, and the larger ice crystals and or those crystals that are more dense will sink more rapidly. And so you get this size sorting impact within these convective anvils that is strongly dependent on the sizes of ice crystals and on the ice density. Yeah, go for it.
So the upper ones do they tend to be more hexagonal? Do they tend to have the lower densities as well?
Actually, the habits of ice crystals is dependent both on the temperature at which ice crystals form, as well as the amount of water vapor available for them to grow in. And so there's actually a very interesting variation with temperature, where different temperature bands in the atmosphere support ice crystals that look like your typical stars that you might draw that as a kid, these sort of snow crystals. So those tend to happen at warmer temperatures, and then as you get into cooler temperatures, they tend to be more columnar or column like in shape. So the temperature in the atmosphere plays a really significant role in determining the kinds of shapes that are produced, and then the amount of water vapor and or supercooled water determines really the sizes that these crystals can grow to.
But that's equilibrium, and this is a kinetic process, and the time scale for particles to change is probably minutes, and these things are evolving on minutes. So I think you can't really make that kind of temperature argument here. So my second question, which is kind of a general one to everyone, is can you think of any remote sensing measurement techniques that could actually measure habits of particles, like some kind of radar system or something, so that we actually get some ensemble statistics on how these vary without just trying to fly an aircraft?
Yeah, that's a great question, and it's a question I would turn back on JPL. I'm a modeler. I'm not an expert in remote sensing techniques, and certainly a lot of our information in this regard comes from aircraft campaigns where people are flying through clouds and, measuring, obtaining, capturing ice particles. From a remote sensing technique, I'll put that back in JPL's court.
So
thank
Evan,
you. This was great.
Hey, Evan, so, the polarization measurements, the polarization measurements of the active instruments like LiDAR and radar give you bulk information about habit. Doesn't give you, really fine granularity information about habit, but gives you bulk information about habit. So that's something that's been used quite a bit over the years, but degree to which you need to know habit, the granularity of detail on habit, I think is an open question. I would think, but anyway, remote sensing techniques typically appeal to polarization in one way or another. So Tom had a question. I'll just pose it for you. It has to do, I think it really touches on the issue of convection aggregation. How do convection clouds modify one another? I think that's what touches on that big hot topic of a convective aggregation.
Yeah, Tom, absolutely. And I didn't cover convective aggregation simply because, in such a broad talk, there's so many different topics, but it's a critical topic. From the point of view that as you aggregate convection and you build systems that are larger in size, these thermals that comprise these systems are better protected from the environment, right? And so if they're better protected from the environment, the impacts of entrainment on these aggregated or these collector systems is reduced. And so if we limit that impact of entrainment on these thermals or these rising updrafts, then we could conceivably expect the updrafts to be better protected and hence more effective transporters of energy, more effective transporters of water vapor, and so on. So this concept of convective aggregation is really critical. It also talks to the extent of convective anvils, which has been, various people in the community have been working on that. It determines the extent of clear air to cloudy skies, which talks to radiation balances. So these interactions and this ability of clouds to aggregate is really critical. I will state we still do not fully understand dynamically what would make clouds aggregate, but it's nevertheless a really important question and concept.
Brian Kahn just notes that, a multi-sensor approach may well help define the habit information as well. So not necessarily just one instrument, but coming up from all different angles. Rob Wood asks the question. I'll ask it, Rob, for you. Are you basically touching on in situ measurements, and are we missing critical in situ obs by not having an aircraft system that penetrates strong convective updraft? So I think the answer is pretty obvious to that one, Rob, but I'll let Sue answer in her words.
So yeah, absolutely, Robin. It's a really important point, and the communities. There's been a lot of discussion in NSF communities regarding the needs for intense storm penetrating aircraft, because we need to make observations, these in situ observations of the distributions in ice sizes and ice types and ice densities. So a resounding yes. But it always comes back to budget and what we can and cannot afford. And I think the view on that is that this may not be happening in the too near future, which is certainly unfortunate when, if you come back to some of the points I was trying to emphasize in my talk, one of our big unknowns with deep convective systems is shortfalls in our knowledge of ice processes. And so somewhere along the line, we're going to have to bite that bullet and say, these are critical. We need to get to information at particle, at the particle level. And somewhere along the line, hopefully someone picks that up and decides that building, deep convective storm penetrating aircrafts is critical and a need to have.
Yeah. Okay. Another one just came in from Sun Wong. Why most rain is produced by moderate systems? He's asking the question, why is a lot of rain produced by moderate systems? Do they live longer, for example, or because of they're more frequent? Why they have such a large impact on the statistics of total rainfall?
Yeah, I think, Sun Wong, that's a good question. And I think the answers to that question, there's multiple reasons for this, right? If you're looking at moderate systems, they typically have weaker updrafts, which means that precipitation of the size of raindrops and or various ice crystals can fall out of these systems more readily. They're not as, they're not suspended as effectively in the upper atmosphere. It also comes back to how long they live and as to how frequently they occur. So it's certainly a very interesting problem. And, from that point of view, precipitation, the most intense storms just don't produce as much precipitation as these moderate storms. So in the most intense storms, their strong updrafts suspend precipitation for a lot longer. They're not as frequent, and they perhaps don't cover as extensive areas. So clearly there's a lot more work to be done on that, and people like Courtney and Steve Nesbitt can provide even more information into the details on that.
We have one more, and I think after this one we might call it quits because we don't want Sue to run out of steam. Actually, I don't want me to run out of steam. This from Xi Gong, and I think it's actually an interesting comment and question. Ice microphysics community is moving towards more detailed Lagrangian tracing of ice particle evolution and their bulk behaviors. Question for Sue is, how many, hang on, this exists in a very small box for me to read. How many microphysics details are sufficient enough within climate models to capture cloud convection precipitation processes? Is more and more complexity, more complex microphysics schemes the ultimate cure? So So it's really sufficiency versus complexity, I suppose, with respect to ice, representing the ice processes. And I'm sure we don't know the answer to that, actually. But anyway, I'll let you answer it, Sue.
I was going to say, do we have an hour? Because there's lots of things to consider here. But you're right in the sense that certainly the microphysics community is, whether you work in ice or whether you work in liquid water, they are moving towards investigating the utility of these Lagrangian tracing type models, where in essence, what that means is you are tracking air parcels throughout storm systems in time, and this allows for a detailed investigation of the microphysics within such parcels by virtue of the environmental conditions that they're experiencing. So there's quite a lot of work being done on it. It's a very interesting approach. But ultimately, this comes down, as the question is posed here, is, is complexity, do we need to go to more and more sophisticated processes? Do we need to ultimately get down to GCM models that are run at 100 meters and that are run with bin, the most sophisticated bin microphysical processes, or do we have to have these Lagrangian tracing approaches within these GCMs? And I think the jury is still out on that, right? It certainly is. There's always the trade-off of computational expense versus sophistication. At one point in time, the whole community was saying, if we're going to do microphysics properly, we need to make use of these spectral bin models. My sense is the community has pulled back a little on that, both because of the computational expense and because we actually do not have the observations with which to appropriately validate how accurate two-moment schemes are versus how accurate bin schemes are. So I think in answering this question, we actually really need to go back to the observations before we can sufficiently conclude at what level of sophistication we need to be at.
Okie dokie. I think Tom, you're going to have the last say, Tom. On the key role of moderate cloud systems, consider the concept of optimal. Hang on, Tom, you better ask this because I'm not quite sure what you're getting at here. Tom, you muted.
Yeah, sure. Quickly, I know there's been some work in the past about area time integral studies of clouds, both from radar and satellites. And as you know, these are part of the cloud clustering. But it seems to me that if the larger ones might be, more counterproductive in allowing the systems to grow in size, the more intense ones. So there may be optimum permitted aggregate of convective clouds. Just a thought.
Yeah, absolutely, Tom, for sure, right? And when we look at our most intense storms, which tend to be really quite often isolated, deep convection, if you consider out here in the mid-latitudes, our supercells is really strong, dynamically driven storms, very intense storms. They tend to, they're not what we would classify necessarily as aggregated. They produce typically less precipitation than our squall line type systems here in the mid-latitude, in which the updrafts are protected, right? They also feed on one another. They dynamically interact, allowing for the system to live much longer. These aggregated systems can actually reach some kind of equilibrium or balance, as in the case of mesoscale convective complexes, of which a lot of work was actually, as you well know, Tom, done here, and you were involved with, MCCs and this. These systems that are aggregated, they can reach this dynamical balance, which then allows them to live for long periods of time, and as such go on to become, both by virtue of their longevity, great precipitation producers, and also by virtue of the fact that they have these protected cores, they're not losing or detraining a lot of their moisture. And so absolutely, that's, you raise a great point that talks in essence to precipitation production by such systems.
Okie dokie. So I would like to thank Sue yet again and for a great seminar. I think we still have a majority of people still hanging on for discussion and so forth, but I think we'll end it here. we'll end the recording here, and thank you again, Sue, and to everyone and all involved. This is recorded, and the recording should be available to everyone. Give us a couple of days to a week to get it through the process of clearances and all that kind of gobbledygook that we have to do. But anyway, we look forward to seeing you again, and applause for Sue. Thank you very much.
Thanks a lot, Graham. Thanks, everyone.
Thank you very much, Sue. Fantastic. You're getting applause now, everyone. Little yellow hands are popping up everywhere. Applauding you, Sue. I would do that, but I don't know how to do it. I don't know how to do it.
It's actually kind of cool. It's really cute. It's
Yeah,
nice to see.
It is pretty cool. Okay. Thanks all.
Okay, Graham. Yeah, thanks a lot. Cheers for now.
Cheers. Bye-bye.